All right. So thanks everyone for coming. We've got Minh-Binh Tran here from Texas A&M. He's going to talk to us today about some recent results on wave turbulence theory. Excited to hear you speak. The floor is yours. Thanks.
Thank you. So thank you so much. It is my extremely great pleasure and honor to give this talk here in the seminar of Caltech, UCLA, and USC. And I would like especially to thank Trevor and you for the invitation. So you is clearly one of the best experts on this topic. So I hope I can benefit from his expertise. So today I'm gonna describe some of our results on wave turbulence theory. So this is the outline of my talk. First of all, I'm gonna give some brief introduction to wave turbulence in both the physical sense and also the mathematical sense. And after that, I'm gonna describe some of our recent work on wave, the derivation of so is this gone? So I don't know what happened. Okay. So it's just the screen just went away. So I'm gonna describe some of our recent results on the rigorous justification of wave kinetic equation, and this is my joint work with Staffilani. And after that, I'm gonna describe the result on the analysis and numerics aspect of wave kinetic equation and also the physical application. So let me give a brief introduction to wave turbulence. So what is wave turbulence? So wave turbulence is a term that appears quite late in comparison to the theory of kinetic, which was in the 18th century, and the theory of wave, which was in the 17th century. So as you know, so if you have wave phenomena, you can have wave equations. So wave equation is the equation that describes the evolution of a wave function. And if you want to say describe the movement of particles, you're going to use the so-called kinetic equations. So those equations describe the evolution of the density function, say of a gas of that consists of particles, and the density function will be a function of space and momentum. So now the question is, what happens if you want to approximate a nonlinear wave system? Then here you have the definition of wave turbulence. So basically, the kinetics equation of wave turbulence describes the evolution of wave energy in the Fourier space, and of course, you have to assume randomness in the wave system. So the first, so there are several fathers of wave turbulence. The first one is Peirce, and Peirce was well known for his contribution in the Manhattan Project. But in one of his first paper, he introduced the concept of wave kinetic equation for an harmonic crystal lattice, in which he wrote the kinetic equation for the evolution of the phonons inside a lattice structure of solid mechanics. And this papers was in 1926 or 28, and this is the picture of the paper. So the ideas of wave turbulence were revived later by Hasselmann in a series of 4 papers in the 1960s, in which he derived a wave kinetic equation for gravity wave spectrum, and this is one of the very well-known result of him for the application of oceanography and climate science. So then after that there was Vladimir Zakharov. So what he did was to derive say a stationary solution for those wave kinetic equation, and so those spectrum, so those spectra was very similar to the Komarov spectra. So people call it Komarov-Sakharov spectra. And this is his book that is quite famous in the field. So let me summarize the physical history of this field. So it has the origin in the work of Peirce and Hasselmann, and the modern point of view came from Newell and Zakharov. So Newell was in MIT and Zakharov was from Arizona. Later, but before that he was from the Soviet Union, and the recent development was done by several people that I mentioned here, but I couldn't, but I missed a lot of name because this field is huge. Wave turbulence has been received very well in the physics community because it has quite a vast range of application, like inertial wave due to rotation, effort wave in solar wind, wave in plasma or fusion devices, oceanography and climate science, or even in quantum physics in a series of work of Yves Pomeau, in which he used the idea of wave turbulence to write the effective equation for the gas inside a Bose-Einstein condensate. So the brief idea is the following. Suppose that I have a wave equation whose nonlinearity is quadratic. So now I take this example of the KZ equation, which was done by Zakharov and Kuznetsov. I have the evolution of the wave function, which is dt of xt. I have a cubic differential operator, so I have Laplacian. So the x variable is in d dimension. So x is x1 to xd, and the Laplacian will be for d components. But I have another derivative which is on x1 only. So this gives a third order differential equation. So I have a quadratic nonlinearity. So I have v squared here, and I have dx1 on this nonlinearity. I have a small parameter lambda that describes the smallness of this nonlinearity. So in the Fourier space, if I do the Fourier transform, so this is a nonlinear wave equation. So there will be a lot of wave interaction. But what the physicist says is that if I look into the Fourier transform at a certain amount of waiting time, the dominant interaction between the frequency will be the so-called three-wave interaction. So K1 will be the wave number that I have. That is the frequency in the Fourier space. So the dominant interaction will be have K1 and K3 combined into K2 in the Fourier space, and our K1 will be split into K2 and K3. All right, so another example that I want to mention is the so-called nonlinear Schrodinger equation. So again, I have a wave function that it depends on x and t. So okay. So I think someone is just removing my slides. So okay, so I have the evolution. So I have I times the derivative of the wave function, and then I have another Laplace operator, and the nonlinearity is cubic. I have a small parameter in front of the nonlinearity. So if I do the Fourier transform and I wait for a certain amount of time, I'm gonna obtain. So this is a nonlinear system. So there are a lot of wave interaction on this, but the dominant one, according to the physicists, will be similar to what happened to the classical Boltzmann equation, in which you have two frequencies collide, and then they exchange momentum and energy, and they turn into a new two frequency, K3 and K4. And in that sense, you also have a kinetic equation.
Sorry, can you explain what the arrows mean? What's the difference between an arrow pointing in and an arrow pointing out?
Can you say it again?
What is the difference between an arrow pointing in and an arrow pointing out of this interaction?
So so what is meaning? Okay, so this is similar to the classical Boltzmann equation, right? So you have two particles colliding. So K1 and K2 are two particles with velocity K1 and K2. They collide, and after the collision, they exchange momentum and energy, and then so the new velocity will be K3 and K4. So in terms of the kinetic equation, K1 and K2 will describe the loss part of the collision operator. So after the collision, K2 and K1 will be disappear, and K3 and K4 will be created. So K2 and K1 will be will be associated to the loss part of the collision operator, and K3 and K4 will be associated to the gain part of the collision operator.
But how is this related to the cubic nonlinearities? How I usually thought would be 3 inputs and 1 output looking at the cubic wave equation.
Yes. So if you write a Hamiltonian, so Hamiltonian will be of order 4. So here you have 4 particles. So this is how you relate that, right? Because you have 4 particles after a collision phenomena.
Okay.
Yes. Does that answer your questions?
For now, I might ask. Just keep going on this.
Yes.
Natural.
Yes. So now I would like to describe the modern mathematical context on this. So this is related to the Bourgain conjecture. So the Bourgain conjecture say the following: suppose that I have a solution to a dispersive PD on a compact manifold. So can we have energy cascade phenomena in which, in the beginning, the energy is focused on the first frequency, and when the time evolves, the energy will focus on the n frequency. So the picture that I draw here, it was taken from a talk by Giglio last year. So in this picture, you see that the amount of water is the same, but water is going from the top to the bottom ladder. So you have a cascade of energy from the top to bottom ladder. Because of course this picture is not really related to the PDs that we are looking at, but it's give an idea what is going on by the energy cascade. All right, so to solve this problem, there are 2 different approaches. The first one is to look into the HS norm. So the energy cascades correspond to the fact that you have a growth in the energy in the HS norm, and there has been a lot of work on this direction. So I would like to mention the pioneer work by Bourgain, Staffilani, the I team, and then Kushkin, Sohinger, Deng, Zhenmeng, Staffilani, and Wilson, and many others. But the focus that I want to mention will be the second one, in which I consider the Fourier transform of the solution of the dispersive equation, and I call it phi hat of KT, and I set AK to be phi hat KT. Now I take the square of this AKs, and I'm gonna get a density function. Then I have to scale the time in a certain way so that we can arrive at a wave kinetic equation. So the evolution of this density function will be governed by a non-local operator of the kinetic type. I'm gonna discuss this scaling in a minute. So the point here is that we expect that the density function of the wave will follow a kinetic equation in which you have the interaction that we have from the beginning. So all right, so now let us go back to the precise form of the kinetic equation. So I have a dispersive equation, and then I want to derive the kinetic equation by taking the Fourier transform, and I take a square. And I scale the time from t to tau. So the equation that I'm trying to look at will be an equation of three-wave interaction. So this equation is the KZ equation, which is the Kuznetsov-Zakharov equation that I mentioned before. So I have the derivative of the wave function will be a cubic operator acting on the wave function, and I have phi square, which is the nonlinearity. I have dx1, and I have lambda, which is the small parameter that describes the weakness of the nonlinearity. So now I have to take the square of the Fourier transform, and I call it nk tau. So I expect that the evolution of nk tau will give me the collision operator that I want. So the equation operator for quadratic a wave equation whose nonlinearity is quadratic is described as follows. So in the previous picture, we have two situations. We have two waves combining into one wave. So you have K2 plus K3 combined to K1. So this is the presentation of the so-called momentum and conservation. So because we want to use kinetic theories, we have to define what is the energy. So the energy will be the Fourier transform, or the symbol of the differential operator here, which is the dispersion relation. So because K2 and K3 they're both combined to K1, then I have the energy conservation, in which I have the energy of K3 plus the energy of K2 is the energy of K1, and this is the delta function. The first delta function describes the conservation of energy. The second delta function is nothing but the conservation of momentum. Now, what you have to do is to integrate in K2 and K3, right? So meaning that you have to consider all of the possibility of decomposing K1, this K1 of the collision operator into K2 and K3. So the nonlinearity here is quadratic. So N2 means that we are considered bring the density function at K2, and 3 means that we are considering the density function at frequency K3, and 1 means that you are considering the energy function at K1. All right. So this quantity is a quadratic nonlinearity, and of course in the picture we also have the situation when there's a frequency K2 that is combining with K1, and that create K3. So then you have another delta function, K1 plus K2 is becoming K3, and this
may I ask a question?
Yes.
So why do you have like the K2 plus K3 equals K1 that can be understood as K1 being the output frequency and is a product of one with wave number K2 and wave number K3. But what is the other one, like the K1 plus K2 minus K3? Because like it's because this phi is real valued?
Okay, can you say it again? I don't
like because because dt phi, if we have the equation dt phi equals phi squared, then if the two input has wave number K2 and K3, then output has wave number K1, where K1 equals K2 plus K3. But how do you have this other way, this K1 plus K2 equals K3?
Good question. So this is because we flip the domain and we consider so we integrate only on the half parts only on the positive part of the domain.
Okay,
right?
I see.
So there are two presentation. One way of presenting is you consider integral on the full space.
Yes.
Another way that you consider it is to flip the domain onto only on the positive part of the domain.
Okay.
The way that you flip it is better because you see that this omega has a singularity at K1, right? So then you want to avoid the zero line.
Okay, I
so
see.
This is why you flip it up, right?
Okay,
But
another
yes.
Another question is, I think probably you're going to explain this later, but I think at some point you mentioned that this delta function is actually not well defined. Like you kind of need to. Are you going to explain this later?
I can explain it now. Okay, so the delta function. The delta function is not very well defined. So for this dispersion relation, you can define a delta function this way. All right. And
Okay.
then why? Because the kernel has a K1 in it. So this K1 will allow you to define this delta function because it has a saturating effect. But if you consider the equation on a lattice, then the effect of the kernel is not strong enough. So you have to do a little bit resonant borrowing. So then in that case, the delta function has to be modified.
Okay, I see. Thank you.
Yes, it's a very nice question. Thank you. So this is a quadratic nonlinearity. So this is why you have a quadratic collision operator. All right. So to summarize, so if you have a wave equation whose nonlinearity is quadratic, you obtain a three-wave kinetic equation in the Fourier space. And if you have a wave equation whose nonlinearity is cubic, we obtain a four-wave kinetic equation in a Fourier space. So now I want to briefly explain what is going on in the rigorous derivation of the wave kinetic equation. So again, I'm going to consider the Fourier transform of the solution of the dispersive equation, and I take the square, and I scale the time to tau. So before that, I mentioned this this scaling, but what is the scaling? So this scaling is following the so-called Van Hoff limit of the kinetic time. So you're going to scale t with tau lambda to power minus 2. So lambda will be the smallest of the nonlinearity. Why is it? So because lambda is the smallest of the nonlinearity. So if you take the square of each of the Fourier mode, then you're going to have a lambda square and on the collision operator. And then the leftover will be of higher order. So you don't want this lambda square, so you just rescale it so that the leftover is of order lambda to the power delta. Delta is positive. So to summarize this, we can say that the nonlinearity is of order lambda. So the rate of collision is of order lambda square. So if we wait longer, then it is expected that we have a diffusion equation, but this is again a big open questions. So the mathematical literature on this is very rich. So it started with the work of Edos and Yao, and Edos, Samhofer, and Yao, in which they started with a random nonlinear Schrodinger equation. So the lambda now is, so because this is a linear Schrodinger equation, so you don't have the nonlinearity. So the lambda will be the parameter in front of the potential, and the potential is now randomized.
Question, can you explain again why there's lambda squared in the equation for the square of the go back on slide. You said that so the nonlinearity is for all of lambda.
Right.
Why does that mean that the lambda squared when you differentiate AK squared? Or I thought from the chain rule it would still just get a lambda.
So I don't really hear your questions clearly, but because of the echo. But
square kinetic equation.
Yes. So basically, we want to consider AK square as the density function, right? So what we're gonna do will be to expand AK. So when you expand AK, you're gonna have one lambda, and then you expand AK star, then you have another lambda. At least as the first derivation. So say you have AK, right? So then you write the equation in terms of the Duhamel expansion.
Yes.
So there will be one lambda in front of the nonlinearity. Now you're gonna multiply that with AK star. So then you have another. You're gonna have to do another Duhamel expansion. So at least you have to do twice the Duhamel expansion, and for each Duhamel expansion you have a lambda square.
So but are there cross terms when you multiply a linear? You can take the linear part of AK and the lambda part of AK star. Do they cancel?
Okay, I don't hear the questions clearly. So
if you take the linear part of AK and the first order lambda term of AK star, you would get a term of order lambda. So do all the terms of order lambda disappear?
So so first you do AK, right? So then you have a so first you have AK star. So AK you do Hammond expansion. So there will be AK star in this guy, and then you do another do Hammond. Then it's going to give you lambda square.
Right, but AK has a zeroth order term as well as a first order term. AK star has a zeroth order term and a first order term. So there should also be first order terms.
Yes. So yes, this is a very deep question. So here so AK will be, we suppose that they are random, and we suppose that initially they're pair. So all of those terms will be, if you take the expectation there, they will be 0.
Okay, got it. Thank you.
Yes. Yes. So that's one thing that I was I didn't say until I explained the reason result. Yeah, but so everything has to be random, because we don't expect to like have a result which is here. So okay, let me so the result of Edos and Yao and Samhofer and Yao was for random linear Schrodinger equation, and at a kinetic time they obtained a Boltzmann equation, and at a later time you obtain a heat equation. So now there was a pioneering work of Bourgain and Spawn in 2010, in which they consider the cubic nonlinear Schrodinger equation, but he put the equation at equilibrium. So they also observe some sort of linearized kinetic equation at a kinetic time. And in the ICM talk of Spawn in 2010, what he said is that there is almost no hope to have a kinetic equation without randomizing the equation. So meaning that we really have to randomize the equation. So let me briefly describe what is going on for the recent work that tried to extend the work of Spawn and Bourgain. So the first work on this program was by Buckmaster, Zhengmang, Hani, and Shata. So in which they derived the kinetic equation, but the kinetic time was not yet. So they fall short a little bit of the kinetic time, and this is the pioneering work in the recent trend. So because the derivation was before the kinetic time, basically they do like they have an equation like this. There was also later work by Kolo, Zhengmang, and Deng and Hani, in which they extended the previous work by Buckmaster, Deng, and Zhengmang, Hani, and Shata. And then the work by Abasolo, Kolo, Zhengmang, in which they try to extend that to the inhomogeneous case. So this is according to Spawn, we need to randomize the equation. So this series of work is for random initial data. So for so there's a different way of randomizing the equation. So in the work by Dimov, Kushkins, and collaborator, they randomize the equation by putting a random noise there. And there's also the work by Fao, which served as an inspiration for our later work. And also there was an extension to the random matrix model by a recent work by Dubak, Zhengmang, and Griffin. So for the recent result, I would like to mention the groundbreaking work of Deng and Hani, in which they can completely derive the nonlinear wave four-wave kinetic equation from the nonlinear Schrodinger equation. So they consider this nonlinear Schrodinger equation. You have a Schrodinger equation, you have a lambda, and the assumption is that the size of the torus is lambda to the power something, and they have a full derivation for the wave kinetic equation in 2021, and then there's also an announcement in 2022 in which they completely completely solve the problem. So in the case of the KZ equation, we also can reach the kinetic time. So the equation that we consider was the one that we mentioned before. So this is the KZ equation, which is the d-dimensional KdV equation, and then we add a noise. So the effect of the noise is the following. So because you cannot define the kinetic equation in a good way, basically the delta function, the energy conservation, the delta function that describe the energy conservation is not well defined. So a noise is added so that it's help with the definition of the kinetic equation. But the noise is very weak. It's just acting on the phase of the mode. So it doesn't add energy or anything else into the equation. And our limit is taken in a little bit different way from Deng and Hanil, in which we take the limit L to infinity first and lambda to 0 later. And then there's also a very nice paper by Ma in which he derived. So the paper by Deng and Hanil was in the continuum setting, and our paper was in the lattice setting. And Ma did the derivation in the of the same equation with the KZ equation, and it was in the continuum setting, and the result was a little bit below the kinetic time, but those are all very nice results. So now this is the summaries of the rigorous derivation, and now I want to move to our second set of results, which is on the analysis of wave kinetic equation. So this is the kinetic equation that we want to study. So our setting is the following. So we consider a three-wave equation. So you can see that here we have a derivative. So there's typo. So this is d tau of nk tau, and we have a collision operator. So the collision operator describes the fact that you have the phenomena when K1 and K2 going and combine to K, and omega K1 and omega K2 is combined to omega. So you have two delta function for this. So the nonlinearity is quadratic because you have a you should start with a quadratic nonlinearity wave equation. So N1 means that you have NK1, N2 means that you have NK2, and means that you have NK. So in this result that we did, we suppose that omega is of a power law, so K to the alpha. When alpha is 3/2, you have the capillary wave. We also consider the case when the solution is supposed to be isotropic. So we identify the density function nk with n of the length of k, and because you have nk is the same of the length of k, and omega is k to the alpha, we can identify nk with n omega, and this is very similar to. So this is basically the same setting that physicists like Pomeau and others consider. So they consider the so-called isotropic case. So what we can prove is the following. So we define the energy of the solution to be the dispersion relation times the density function. We call it G. So there will be a blow up time tau 0, such that at time tau 0, there's a blow up. So you can decompose the energy into a regular function and some delta function at infinity multiplied with the weight. So what we can see is that originally the regular part is 0. The regular part is a normal function, it's non-zero. The singular, the measure part is g theta is 0. But when tau is going to infinity, this g part is strictly increasing, strictly decreasing, and this g theta tau is strictly decreasing. And when tau tends to infinity, all of the energy will be accumulated into the g theta tau part, while the g bar part is going to be 0. So we observe this, and we call this as an energy cascade phenomena, in the sense that we see weakly that the energy of the kinetic equation is accumulating and finally it's arrived at the delta function at infinity. Of course, to say something about the wave equation is still a big question, but at least at the level of the kinetic equation, we see something like this. And we also see an energy cascade rate. So we see that, okay, so this G bar is going to 0. We have velocity for that. This is bounded by 1 over square root of t. And the question is it optimal? So in our work is inspired by a previous work by Escobedo and Velasquez, in which they also observed something similar for the four-wave equation, and there's also a related work by Germain Diate in 2020.
Sorry, can I ask, what do you mean by like omega, the delta function at infinity? What is the like? Okay, first of all, what does this mean? And second, like, what do you mean by blow up? Because you said the solution exists for all the time, even bigger than tau 0. Then what do you mean by blow up?
Excellent. Yes. Okay. So what is meant by blow up is that, so the solution is in the measure sense, right? So you have a solution in you have a global solution in the measure sense, but the blow up means that the regular parts is blow up. So so you have a loss of energy of the solution, right? So the blow up is for the regular. If you consider the regular solution, the regular solution will survive up to tau 0. Okay. Now, if you want to consider a measure solution, the measure solution survive for infinite time. And this is what the result means. The result means that, okay, so there will be a time for which the regular parts doesn't exist. So it's going to be decreasing. And then the singular part is going to grow. And if you consider this G bar only, and you want to consider energy conserving solution, then it's only up to tau 0. All right. Okay. So what happened is that some of the energy of G bar will be lost into this function. And what is the delta function at infinity? So we compactify the domain, and we suppose that infinity is one point that is acceptable. Okay.
Thank you.
Thank you. This is very good. This is really to the point. Rapid result. All right. So now what we want to see is that, okay, the energy cascade rate is bounded by, so this, we know that the energy of G bar is decaying, and the decay rate is bounded by this, and we want to test if this is optimal because we don't have the lower bound. So so this is the motivation for the numerical parts of our result. So the first result that we obtained was by using a finite volume scheme. We use a finite volume scheme because this is one of the most famous scheme for coagulation equation. So for coagulation equation, so basically the coagulation equation is describing only the one part of the collision operator. So the coagulation equation describes the chelation of blood. So what you're going to have will be, okay, you have two blood particles that combine into one, and they don't. So the fact that one particle is split into two doesn't happen, right? So basically, we only have one part of the collision operator, which is the loss part, and there's no gain part. So the coagulation equation is quite famous in medicine because it's described one of the most important phenomena, which is the chelation of blood. And now because you only have the gain part, the loss part of the collision operator, you're going to have the chelation, and then for those coagulation equation, the numerics was well developed. So this is the reason why we took one of the scheme that was quite famous in those community by Francis Finber and collaborators. So what we did was that, okay, we mimic this scheme, but we have to extend that because in the coangulation equation, you don't have the gain part, you only have the loss part. So so then you have to manipulate something so that it works for both parts of the collision operator. And after that, we took an initial profile like this, and we plugged that into the scheme. So what we saw was the following. So we saw that the theoretical rate, so this is a straight line because we take the log. So the theoretical decay rate was the straight line, which is 1 over square root of t, and the numerical one was this orange one. So it is quite precise what the theoretical rate was obtained. So to be sure, we then implement with so Bensoussan is an expert on stochastic optimization and control. So then we learn from him, and then we do a neural network approximation, and what we see, it will be this profile. What is going on in the machine learning scheme. So you have the blue one, which is the initial condition. Then in time, it's going to be string into the orange one, and then if you wait a little bit, it's going to. So this is the regular part of the solution. So for numerical scheme, you cannot see the delta function. So basically, this is what we observe is just the numerical part of the regular part of the solution. So we see that the solution is the energy of the solution is decreasing, and we plot the decay rate. So you see that in the beginning it's perturbating a little bit, but when time increase, the shape of the decay rate, which is in blue, is almost parallel with the orange one, which is the one coming from t to the power -1/2. So both schemes also kind of agree with what we predicted in the theoretical proof. So now because wave turbulence has application, it is originated from the physics. So then we want to come back to the physical application. So as we discussed before, we want this is my work with Pomeau, and he's an expert in those kinetic theory for both Einstein condensate. So what happened is there was a discussion between Bose and Einstein in the beginning of the 20th century. So Bose asked Einstein, so you have a glass of water, you put the temperature of the glass of water to 0 Celsius, then you have a phase transition, which is solid. You have ice. So what happened if you do the same thing for the photon of light? So Einstein said that, okay, so you're gonna obtain a new state of matters, and people nowadays call that the Bose-Einstein condensate. So the Bose-Einstein condensate was mystery until very important work by the MIT and the JLA lab, in which they realized the Bose-Einstein condensate in the lab. So what happened is the following. So this is a picture that I took from the lecture of Ketterly. So first, at high temperature, you're gonna have particles that are moving. So they are like balls, they're like billiard balls, and the distance between them is d. So when we lower down the temperature, they're gonna have a wavelength, which is the Broglie wavelength. So the Broglie wavelength will increase when the Broglie wavelength is when the temperature is lower. The Broglie wavelength will be increased, and when the Broglie wavelength is the same with the distance between the particles, you're gonna have the matter wave overlap, and this is the so-called transition temperature Bose-Einstein condensate, in which you see the Bose-Einstein condensate and some thermal cloud above. When the temperature is absolute zero, you see a pure condensate, which is when Zion matter, which is the so-called Zion matter wave. So now the situation that we are interested in was the situation when the temperature is between zero, absolute zero, and the transition temperature. So you're gonna have a coupling between the big Zion Bose-Einstein condensate and a thermal cloud. So the wave function of the condensate will be described by the Gross-Pitavsky equation, and the thermal cloud will be described by a kinetic equation. And surprisingly, the kinetic equation has a very similar structure to the 3 and the 4 wave equation. So the first work was done on this topic was by Kirkpatrick and Dorfman in '85, but at the time there was no experiment on Bose-Einstein condensate. So this paper was kind of forgotten. And after the realization of the Bose-Einstein condensate, there was 2 work that tried to follow the path of Kirkpatrick and Dorfman to derive the full system. I mean, basically they follow the same step. They just write in the better way. So there was a group by the Zing people and the group by Pomeau and his student and postdoc. So what happened will be the following. So in the thermal cloud, there will be the cases when you have two quasi particles that collide and combine into one, and one particles which is split into 2, right? So this is similar to the 3-wave situation that we discussed before. And also there is a situation when you have one wave colliding with another wave, and this is split into another 2 wave. So the 3 waves in the quantum context, this is called C12, and the C22 in the quantum context was called C22. But then there was questions that was observed by Linda Rachel and her student Gus, in which she observed that because the Hamiltonian is of order 4, why don't we have the situation when one wave is split into 3 and 3 wave is combining to 1? So this was so her conclusion is that you're gonna have to add a new collision operator into all of the interaction, otherwise it's not true. And she has some experiment and test that with numerics, and she observed that if you observe some of the parameter of the Bose-Einstein condensate, like the viscosity and those kind of things, so if you don't add C31, the result of the experiment cannot be explained theoretically. But if you add C31, then the result obtained by the experiment can be observed by the new theory. So however, the paper by Rachel and Gus was not published because her computation was done by hand, and it was like 40,000 in video terms, and one need to do all of the bracket, and it turns out that the computation is like one suitcase, and so this is why this is not possible to check. So after that, with Pomeau, we can redo the computation, and we reduce the number of terms from 40,000 to 30 terms, and then the appearance of C31 is quite it can be checked by just 15 pages of computation. So thank you so much for your attention.